So while people are still coming in, let us remind ourselves what what did we say last time about the Poisson bracket structure or Hamiltonian structure of ideal hydrodynamics. So the equation of ideal hydrodynamics can be derived or can be thought of as coming out from a Hamiltonian, which is sum of the kinetic and the potential energy. Sometimes we also use the following notation. Pi is the momentum density. And so this term can be written also as pi squared over 2 rho. With the Poisson bracket, which I would write like this, rho is equal to 0. Bi x rho y is the derivative of the delta function. And the velocity do not commute to the vorticity times the delta function. And we said that the equations can be of hydrodynamics can be written in a very familiar form from classical mechanics. Basically, we have x dot rho equal commutator of Poisson brackets of h with rho, and v dot is the Poisson brackets of h with v. And you can check by direct calculations that the first equation is nothing but the continuity equation. The second equation is conservation of momentum, also called the Euler equation. This is continuity. This is so-called Euler equations. Okay, so today I'm going to tell you a little bit about this some curious fact about these Poisson brackets that would put it in a broader context related to quantum field theory and also to differential geometry. So the first thing so these Poisson brackets looks a little bit random the way it is written here. I'm going to show you that actually they do make sense. So the form that I will need to use is slightly different from this. So I'm going to write these Poisson brackets between the momentum density and the density. So rho x di delta x minus y, and then I have also pi I pi j. These are equivalent to the form that we have written in the previous transparency. Pi j of x d over dxi minus pi I of y d over dy. I'm writing this in a little bit of a random choice of notations. In fact, this d over dy can be exchanged to d over dx, derivative of this delta function with respect to y is equal derivative with respect to delta function over x. And chosen to write this second commutator that way to make sure that it's anti-symmetric under exchange ix to jy. Second, you can see that it's anti-symmetric with respect to exchanging the first and the second and second factor in the Poisson bracket. So let's make the following observation. If I introduce something that I call vector P integral over the whole space of the momentum density, or it is just integral over x rho v. This is the total momentum. And let's check how the Poisson brackets of P with some quantity looks like. For example, I can take the first Poisson brackets and integrate over dx. Then I would have pi I Poisson bracket with rho y, right, equal this integral over dx, rho of x, d over dxi, delta x minus y. It's a vector. Right. And then I can do integration by part, pushing this dt here using the delta function, integral over delta function, set the parameter, set the x to be equal to y. So rho of y with a minus sign. Minus sign. So that one already knows about some fact about quantum field theory that should look familiar. The word attached to this formula is that the total momentum is the generator of translation. So when you in quantum theory, that means the commutator of this operator with any operator is the derivative of that operator. So here is the Poisson bracket of the version, the classical version of that. One can also check that for the from the second formula, just integrate both sides over x, pi, the second commutator on the top, pi pi commutator with pi j of y, right? Okay, so here I have to be a bit more careful. So the first term, integral dx, pi j of x, d over dx, I delta x minus y, minus this integral dx, pi I of y, d over dy, j delta x minus y. This one can be computed in the in the first term. I get derivative, right? The second term is even easier. This pi here does not depend on x, so I can put it outside of the integral. We have integral of the derivative of delta function, which is 0. So it is 0. So in particular here we see that this when I have derivative of the delta function, I have to be careful what multiplies it. So here, for example, I cannot, although here I have looks like a delta function, it cannot replace this pi I of y by pi I of x. The result will be different. So that's why I have been careful to keep the to write down the variable here. And so again, you see the final result is that pi I commute with commutator of pi I or Poisson bracket of pi I with the momentum density also give minus the derivative of momentum density. So it can be generalized. Anything that one can construct from rho and pi satisfy this equality. in hydrodynamics, in this Poisson algebra of hydrodynamics, the momentum density plays the role of the translation operator. Okay. That's the first thing. But there is even a richer structure behind this Poisson algebra. Let me take the integral of over momentum density with certain envelope function of certain weight. We call that psi x pi I of x. So if psi I is equal to x equal to 1, I get back the momentum density. But here, if psi is a function of x, it's now no longer a total momentum. Some kind of object. And one can ask, what is the commutator of that object with other quantities? So let's try to do that with rho and see what happens. I know that pi x rho of y from the previous page, d over dxi delta x minus y. And so this operator, let me call that, for the lack of the notation, p of psi. That's p psi rho y. That commutator is integral dx and then psi I of x rho of x d over dxi delta x minus y. Integrating these things by part, we get d over dy I of psi rho. Okay, so now I need to tell you a little bit about differential geometry to interpret this formula. So this part of differential geometry is usually presented in the first few lectures in the general relativity course. It's rather rudimentary. So differential geometry. So in differential geometry, we have a notion of the system of coordinate system. So I'm going to just consider differential geometry of space, not space-time, as in general relativity. So the coordinate, spatial coordinates, we are dealing with some kind of three-dimensional space, which for the purpose of this lecture can be just taken as the flat space, three-dimensional flat space, but the coordinate system may be curvilinear. So coordinate system xi. Right? It's the way we attach each point to three coordinates. And in differential geometry, we have a notion of coordinate transformation. So under transformation, we go from one coordinate system to another coordinate system. We call that xi prime. So here I go 1, 2, 3. Here I prime also go 1, 2, 3. But the coordinate system I prime may be different from x, so it may be a different way of drawing this line. And x prime would be a function of x. Normally, doesn't have to be any particular form. That's the power of differential geometry. One doesn't need not need that to be, for example, a linear function. Under the coordinate transformation, one defines how different object, different tensor transform. So a scalar transform in a rather simple way. Phi of x go to phi of x prime, phi prime of x prime, which is a function defined so that it's equal to phi when we replace x prime of x. So basically it's the same function, same dependence over space, but written in different system of coordinates. Just here it's just the meaning of this formula is just replacing old coordinates by new coordinates. Okay. Now there are two. There's some kind of tensor, but first consider vectors. There are two kinds of vectors. There's covariant vector. Covariant vectors has an index I that we put as a subscript. It transforms under general coordinate transformation in a particular way. When we have here x I e x I prime a I of x, and this factor in front basically make sure that locally we can think about this coordinate transformation. It's some linear transformation. This is the matrix of the linear transformation, and the way that the indices are put here is that there is the summing is over a pair of an upper index and a lower index. There is also the notion of contravariant vector that has an index that is on top, ai of x, go to ai prime x prime di xi prime over dxi ai x. So so here again the indices have to be consistent. Upper index I prime matches with upper index I prime on the right hand side. D over dxi basically derivative over x with the upper index make it a lower index. No, this I here is in the wrong place because the index of this contravariant vector is the upper index. And similarly, I can define tensor, etc. But I'm not going to write here. With a two-index tensor, you have two factor in front. There is also a notion that is going to be useful for us here. Any questions so far, actually, for this? Or I'm going too fast? Let's talk about something that's a little bit less used in general relativity, but the notion of scalar density. So density is something that one can take integral over. So that's how the formula is written. The the scalar density transforms slightly differently. Transform to phi prime x prime equal not to phi x, but to the determinant of the Jacobian of the coordinate transformation. And the reason that we write like we have we call that scalar density is that because the integral is unchanged. Integral of a scalar density over the whole space remains the same after integration. So here, the reason why that's so, you recall that x prime, when we go from x prime to x in the integration, we need to put a Jacobian. This is the Jacobian of the transformation from x prime to x. Phi prime of x prime is again this Jacobian, but it's a reverse Jacobian. The product of these two Jacobian is 1. And so that's why this quantity is called the scalar density. So scalar, there is also notion of vector density. It's defined the same way. The vector density AI of x goes to AI prime x prime, which is equal to that Jacobian times the factor that has been there already, and then AI x. All that notions can be defined for any manifold. This is the first step. This is the first step toward theory of general relativity. Actually, the next crucial step that we will need is the introduction of a metric on the manifold. That we're not going to need. Let's consider infinitesimal transformation, coordinate transformation. These are transformations that take us from xi to xi prime equal xi plus some very small function. Xi very small. I don't know what small compared to, but let's say small. Small compared to anything that we need it to be small compared to. So then we can ask, how does the different, say if I have a scalar phi of x, go to a new scalar phi prime, define so that phi prime of x prime, but x prime is x dot c equal phi at x. I. That was the definition, but sometimes it's more convenient to think about phi prime as with the argument x instead of a new argument x prime. So if you think about phi, this transformation is transforming one function to another function. Phi prime of x should be equal to phi of x minus c, right? Which is phi of x I minus x c I di phi. Right. Okay, so now a scalar density for the scalar density, we just need to multiply the whole thing by the multiply that by the Jacobian of the transformation. So these Jacobians have to be computed. So this is the things that is dxi over dxi prime. So they are close to each other, and it's a matrix whose it's almost like delta ij matrix minus x equal, so x equal x. So I have here x equal x minus c. So here I have minus d. So I prime, well, this I prime, right? And then I prime ci. It's almost a unit matrix with very little change in the elements. The determinant of such a matrix is just the basically product of the diagonal element. So in the scalar density case, all we need to do is to multiply that thing by the determinant here, which is 1 minus di psi I. That is the determinant of the Jacobian transformation. So it's roughly phi minus psi I di phi minus phi di psi I plus dot dot dot. That's the how the density changes. Okay, so a little bit maybe a little bit words we can put in here under coordinate transformation is like a infinitesimal coordinate transformation is like a spatial translation, but we translate the system by slightly different amount at different point. So this C is, so here I have some kind of coordinate system that let's assume it's even assume it to be this Cartesian, and then at each point we shift the point by an amount equal to C, right? And here the formula for the scalar simply means that we just have derivative along the direction C. For the density, the change of the quantity is also has a part that basically tells us how whether we have compressed, how much we have compressed the coordinate system. dxc, dxci is the amount, the amount of compression that we have done, or dilatation. Okay, any questions so far? No? So let's look back in our formula that we have here. Maybe I just rewrite it here. We have said in hydrodynamics, we have computed the commutator of the operator, which is, I have to be careful, psi I of x, pi I of x, the Poisson brackets of that with our say density at point y using the Poisson brackets. We found it to be minus di psi I of rho. Okay, rho is computed at the same point as rho here, that is point y. That is rho minus rho d psi minus ci di rho. Okay, so now interesting things happen. See this, a scalar density under infinitesimal gauge infinitesimal coordinate transformation is shifted by the amount, this small amount written here on the at the end. This is just equal this is just equal, what we find is just equal to the shift of a scalar density under infinitesimal coordinate transformation with parameter xi. Very pretty curious, isn't it? We have that fact. And also, if you compute now the same thing, we just use our previously introduced notation of that as P of xi, compute P of xi with pi I. I encourage you to do these calculations. You find that it is equal to minus xi j dj pi I minus, let me see, I've done this calculation, minus pi I pi j dixj minus di xi times pi j I, something like that. And again, this is one can check from the formula for the transformation that give us the transformation properties of a vector. The transformation of a vector density under coordinate transformation, that nothing but the change of a vector density pi I under infinitesimal coordinate transformation parameterized by xi. That's AI, this vector density in AI goes to x to AI prime, x plus xi equal this Jacobian times dxi dxi prime dx, so dxi ai prime ai prime, some formula that we've written before. But if you expand that in xi, right, considering not a general transformation but an infinitesimal one, you'll find this change of the vector density be exactly equal to the commutator of P with of this operator we call Pxi with this quantity. So again, this there is a curious connection of the hydrodynamic Poisson algebra with infinitesimal coordinate transformation in differential geometry. As far as I can find, this was written down first in an article by Jaloshinsky and Volovic in 1980. I put that article in the files in the file section of the Canvas. So that's interesting, but it's also useful because a lot of time when we do calculations in of the Poisson bracket, the calculation is simplified if one just think about what the quantity is supposed to transform under coordinate transformation. Any questions so far? Okay, so let's try to, let me give you one example where this interpretation of the Poisson algebra can be useful in practical calculation. So let's consider now 2 plus 1 dimensional, 2-dimensional hydrodynamics, ideal hydrodynamics. That's the we have rho Vx Vy, so it's V1 V2 written in terms of rho V1 V2. With certain Poisson brackets that exactly the same as before. Now in 2 dimension, the vorticity is now not a pseudo vector but a pseudo scalar. D1 V2 minus D2 V1. Okay, so now that can be written in the following way, using the rule of Einstein's. Put the indices so that the upper index sum up with the lower index. Okay. So now let's try to compute the commutator of omega in the Poisson brackets that involve omega. So one thing that one can do right away is the commutator of omega with rho is pretty simple. Right? That's because we have the following things. We have Vi, the commutator of Vi rho j, that is rho y is derivative. Okay, so actually in this lecture I'm going to be pedantic and put the index of V always at a lower index. Velocity here is actually a covariant vector. So if I now need to compute omega, I need to take the curl of this. So I take curl of this, but curl of but this is a gradient. Curl of gradient is 0. 0. In other words, it would be something like epsilon ij di dj of the delta function, which is 0. So the vorticity commute with the density, that's actually universal. It's no, it's valid for all dimension. Now let's try to compute the commutator of omega with V, because commutator with rho is already 0. All we need to know is the commutator of omega with pi, right? Pi of x, omega of y equal what? That would be next thing we need. But it's much easier, as we have discussed, to think about this as particular case of the operator we call pi xi, commutator of p psi with omega, right? In the case of psi is say a delta function, then we get just the density of momentum at one point. So we can just try to compute this commutator, this Poisson bracket. And that means that what we need to do is to analyze the how this quantity transform, how it's transformed under coordinate transformation, infinitesimal. coordinate transformation. Okay, so there is various things that also from differential geometry that we need to know. So if AI is a tensor, or let's say it's a vector. In this case, a vector, a tensor with one index is just called a tensor. So if AI is a vector, then generally its derivative does not transform like a tensor at all. And that's very easy to see. If I have AI transform the AI of x, go to AI prime x prime equal dx I over d x I prime a I of x, right? Suppose I try to take a derivative and see whether the derivative of one side transform into the derivative of the other side. I will take derivative of this with respect to x. Let's say j, right? AI x. This is, I call that ej AI of x, right? Then this becomes somewhat mess on the other side, because the derivative with respect to x prime, the same quantity on the right hand side, a similar quantity which is d over dA dx j prime of a I prime of x would actually have two different parts. The derivative over x prime can act here or here. There are two different terms. One term is dxi when it acts on a using the chain rule. I can rewrite its derivative of aj divided by x j prime d ai over dxj. But there is a offending part. AI. Now, if the first part was the only thing, then we would say that the derivative transformed like a tensor of second rank. Tensors with second rank transform in a similar way as a vector, except that in addition to one this matrix dx over dx prime matrix, we have two factors. But the second part prevents the derivative of the vector to be a tensor. So usually, the way one deals with this question in Riemannian geometry is to introduce metric, and then there is a operation of parallel transport, etc. That's outside our sphere of concern. What we notice here is that this factor cancel out if we are taking asymmetric, the anti-symmetrized version of the derivative. So if you take, instead of diaj, you have diaj minus djai. It's a tensor. Asymmetric derivative of a vector is a tensor. So curl is still a tensor in this sense. And so this omega, this d1, this divj minus djvi is a tensor of second rank. That's good. It's the tensor. It's easy to see how it transforms. But there are one thing here. It's also this epsilon ij. Epsilon ij is the thing that equal to 1 if I equal 1, j equal 2, and equal -1 if I equal 2, j equal 1, and equal 0 otherwise. So now this, I'm going to just leave it out as a check that you can do on your own. This transform like tensor density. So if you take this tensor that has component 1 and -1, transform it to another system of coordinates, still 1 minus 1. If you declare that the transformation law looks like a relevant transformation law for a tensor density, that is, it has this prime I d x j prime dj, and then there is Jacobian, relevant Jacobian. So that means now there is another rule. When we take two tensor and then sum up over indices, we again get tensor. Or if one of them is a tensor density, then we get the other quantity would be also transformed like a density. In this case, Vj minus dj vi, this quantity is just a scalar density. So omega transforms like a scalar density. So if it is a scalar density, we can, it would transform in the same way as rho. Rho also is a scalar density. And from this, there is a very important lesson. So first step, we find that omega over rho is just transformed like a scalar. Take two density, divide to each other, it becomes scalar. When one transforms it, the Jacobian cancel, the Jacobian from the denominator and numerator cancel each other. It's a scalar. Okay, why is it important? I want to construct, I would like to construct conserved quantities, things that would be preserved under coordinate transformation. So let me show that if I have quantity that looks like this, integral over x, like rho times any function of omega over rho, f, any function, then it would be conserved. In fact, it's not only conserved, as we were going to show, it's also a Casimir. That is, it commutes with everything. It's actually Casimir. of the algebra, of the Poisson algebra. Is in 2-dimension hydrodynamics, we claim there is an infinite number of Casimir C can be a function CF. If this F can be anything like linear, well, if F can be taken to be, so for example, omega over rho to the power of n, and we would have infinite number of these quantities that we claim to be commuters. Oh, n equal to 1 would be integral over the vorticity. That is rather trivial because its vorticity is derivative, so integral equal to, that integral will be equal to 0. But otherwise, it's a non-trivial operator. Okay, so how do we, I'm going to show that. So let's recall that rho equal rho omega equal to 0. And so that means rho has to commute with any operator C, commutator rho with any C is 0. Okay, now rho, commutator of rho with V, right? I'm all I need to check is the commutator of P with C, F. P of C, that's the operator of coordinate transformation, infinitesimal coordinate transformation, under which, so maybe I do that on the other page, under which we know that rho, for example, transformed like a scalar, so that is minus Ci di rho minus rho di Ci, and that if the quantity is a scalar, that's like any function of omega in n, the transformation would be like minus C d rho di of f omega over rho. So xc commutator with this integral of rho f omega in rho. Then we can write down minus integral dx minus Ci di rho times f minus rho dx Ci times f minus Ci minus rho Ci di f, but it's nothing but integral dx di of plus Ci rho f to 0. In other words, this is just very trivial factor explaining what we have a quantity here, rho times f is a scalar density. You take scalar density, integrate over space. That the way that we have defined the transformation law is so that the integral over space over scalar density is invariant. So we have just checked that it's invariant explicitly. So this one is a scalar density. And so that means that in 2-dimensional hydrodynamics, and there is a infinite number of Casimir, which can be thought of as, say, you can write down any function for rho, any function at all of omega over rho, would be things that commute with any things in the algebra, including the Hamiltonian. So this C of F, including the Hamiltonian, so C of F over dt is automatically 0. The statement is even stronger than that. Last time we talked about 3 plus 1D. Three-dimensional hydrodynamics. And we also touch upon the existence of a Casimir there, but the Casimir there is only one. It's integral of V time, it's basically V dot omega. Omega is a vector in 3 dimension, vorticity. This commute with everything in the algebra. I think the way that we did last time, we show that it can be shown directly, but we did that through a trick. We wrote the Clebsch decomposition of V in expressing it in terms of 3 variables, theta, alpha, and beta, and then we rewrite this as integral dx of gradient rho times gradient alpha cross gradient beta. And it can be written as a surface integral over some surface instead of alpha plus beta, something like that. Since it's an integral on surface, we choose a surface, and if the operator is evaluated inside the surface, of course the commutator with something that exists only on the surface would be 0. That was what we did last time. So this is also a Casimir in 3 plus 1 dimension. But you see here there is a difference between 2 and 3 dimension. In 3 dimension there is only one Casimir. This V. And here it's an infinite number of Casimir. So what is it related to? Why is it so? Remember that this Poisson algebra. So let's look at the Poisson algebra. Say in 2 dimensions. So in 2D, it involved 3 fields: rho, Vx, and Vy. Okay, it's actually odd number of fields. So the fact that it's odd means that it's like saying that the phase space has odd dimension. You know that it cannot happen. A phase space in classical mechanics has to have the even number of dimension because it's involves the coordinate and the conjugate momenta. Right, so you have a system of n particles. The phase space would have dimension 6n, not even dimension. So here we have a phase space that is even dimensional, and so that means that this algebra cannot be reduced to canonical form. In other words, it cannot be reduced to canonical form. So it must be degenerate. It has to be degenerate, and that means there is this means the existence of the Casimir. One simple example of that phenomenon, it happens when you look at the algebra of rotation, spin commutator in quantum mechanics. So we know that the spin, the commutation relation of the operator of spin, or can take, for example, that to be total angular momentum or orbital angular momentum. So for spin, we have some commutation relation like that. You can think about that in the classical level, would be defining some kind of Poisson algebra with three operator as x, as y, as z. So it's the same phenomenon. And the phase space here has even dimension, and that means that there is a Casimir. That is, you can think about that in terms of the of a sphere. Actually, the radius of the sphere x square commute with everything. And if I think about this x s as transformation on the sphere, it doesn't take a particle outside the sphere. So in 2 dimensions, then the fact that we have three sets of fields instead of an even set of fields seems to be related to the existence of an infinite number of Casimir.
Sorry, I just have a couple of questions very quickly.
Yeah.
So the fact that the vorticity in 2 dimensions is a scalar density is because we're using the Levi-Civita symbol instead of the Levi-Civita tensor to define it. Right?
There is no tensor. There is no Levi-Civita tensor that one can define. In GR, usually you just write epsilon ij is equal square root of g, right? Or 1 over square root of g, I forget. 1 over square root of g, I think. But there is no g in hydrodynamics. There is no no metric that we.
But if we're working in flat space, can't we always define a metric as the one induced in whatever coordinates we're working in upon transforming from the Cartesian coordinates?
That would be that would be a separate quantity. It doesn't appear in the Poisson algebra at all.
I see.
When we write down the algebra, you have only these. These are the only things that are available.
I see.
Rho, yeah, there is one volume. There's rho that transforms like a volume form, or it's transformed in the same way as scalar density. So one can, but there is nothing besides rho to define.
I see. And my second question is, so in 3+1D, v dot omega should, how does omega end up becoming a vector instead of a vector density?
So so omega here is actually a vector. I think it's let me think. Omega is defined again like this. So omega ij, right? So let's say omega I is epsilon ijk djvk, and so that is a density,
right?
And this is a tensor. So omega I is contravariant vector density.
But then can't we do something similar where we take v dot omega and divide it by rho and take any arbitrary function of that? What goes wrong with that in 3+1D in order to get, say, a Casimir?
It will not commute with rho. I think it will not commute with rho because
I see.
V and rho commute to non-zero things.
I see.
So rho commutate of dx, rho f v dot omega over rho will not be zero.
I see.
Yeah.
Thank you.
Yeah.
I had a quick question regarding the example you provided with the spin. So in the spin example, you start with these 3 generators. and then lo and behold, there's one Casimir. Is the difference between that and the fluid or the hydrodynamic example we just did, where we start with 3 fields and we get an infinite number? That's just because we have fields, right?
Yeah.
Okay.
This argument, I actually don't know whether I can make it, how to make reverse. Basically, you have an
I see,
infinite
okay.
number of degrees of freedom, though it's a 3 fields. So
I see.
it would be nice to have a field that like a Casimir field. So here it's a Casimir, still not a field, but a Casimir depending on a function.
I see. Okay.
Yeah.
And then I had a bit of a philosophical question. I'm not even sure if there's a sharp answer to it, but the from the outset of how we construct the hydrodynamic theory, the mantra was, all right, let's find all the conserved quantities and then associate with those, densities, and currents and stuff. But here we're finding actually there's a lot more conserved quantities. And so did we miss those at the beginning, or are they in some way not independent from the ones that we identify when we construct the hydrodynamic theory?
So these are not, these are in some sense like a emergent and approximate conserved quantities. They are what emerges in the low energy description, in long distance description, not the fundamental conserved quantities, and they are not even exactly conserved. If I put in some viscosity into the equations, then they would dissipate. Yeah, we can see you can actually compute, but the rate of dissipation is going to be proportional to the viscosity itself. It's not a.
That's right.
Yeah. But it does have some interesting consequences in the situation in which the viscosity is small. So, for example, in turbulence, problem of turbulence, there is an intermediate scale in which the effect of dissipation is small, and in these intermediate scales, we can talk about the cascade, the transfer of over length scale of these quantities. So this helicity, for example, or the in 2 dimension the vorticity, like, yeah. So the important thing in 2 dimension would be when this function f is equal to x squared, so it's integral of omega square is conserved. If rho is constant, also for incompressible hydrodynamics, it's just integral of omega square.
San, I wonder if you may clarify. I have some very vague recollections about subtlety on how you label the particles and the invariance and the relabeling of the particles being related to the Casimir. Is this a complete mirage of my?
No, I don't think so. I think it's related, but I remember the word, and I think I have to think a little bit more about that. But there is a different way of thinking about Lagrangian theory of the fluid, in which one described the state of the fluid by giving the coordinates of each of these particles, and I can try to work it out and then
maybe it's not relevant.
Give it to you. I think I heard the word, and I think in principle there can be it has a meaning, yeah. But I haven't checked myself.
Sorry, I have a very naive question. So I'm wondering for the dissipative hydro, for example, if we consider the bulk viscosity, Is it possible to like slightly modify the Poisson bracket to gather this similar Poisson structure in this case?
No, it's in principle not possible to include dissipative effect into hydrodynamics, into Hamiltonian formulation like this. It's because of the you see, if I have that, then the if I start hydrodynamics from some initial condition and wait long enough, then everything will becomes thermal equilibrium. That is a state where rho is a constant, v is equal to 0. So it's nothing happen at the end. And so if such a Hamiltonian formulation occurs, then the equation would also have to have this convergence properties. Every initial condition under the Hamiltonian evolution converges to the same point. But remember that in Hamiltonian formalism, there is a Liouville's theorem. So Liouville's theorem tells us that if you take some volume in phase space, evolve it in time, that the shape of this volume may change, becomes complicated, but the volume itself doesn't change. So that forbids the process, the convergence of all the initial condition to a thermal equilibrium.
Yeah, I see.
So it's not possible. This Poisson brackets is convenient because in many cases, as we see maybe later with superfluid hydrodynamics, for example, it gives us a shortcut to the construction of the non-dissipative part of the equation, and then adding the kinetic coefficient one can do later. You can put them by hand.
I see. Thanks.
Sorry, just a very quick follow-up to that. So there's an obstruction to writing dissipative hydrodynamics as a Hamiltonian theory, but is there a way to be like, do we know more precisely where that obstruction is, whether there's an obstruction to writing a Hamiltonian or to constructing a Poisson algebra for the variables, or both?
So strictly speaking, now I'm going a bit maybe aside. Strictly speaking, there must be some way to do that. So philosophically, we have some microscopic theory, and usually actually the prejudice or the view at least in particle physics since Weinberg's paper in 1975 is that there is some kind of low energy effective theory that obtains by some philosophically integrating out the high energy degree of freedom of the hard mode, taking a path integral. So now that's important because this procedure assumes that we have to be able to formulate the microscopic theories and path integral. So now remember that we are dealing here with a system at non-equilibrium at non-zero temperature. Right? So path integral in non-zero temperature is tricky. There's two formalism. One is a Matsubara. Matsubara formalism allows us to write down the partition function as the Euclidean path integral. But that's completely inappropriate. It's will not give us any information about real-time evolution. So that's Matsubara formalism cannot be used. The second one is the Schwinger-Keldysh formalism. That formalism, one writes a theory as a contour integral over a double contour, so-called Schwinger contour. Keldysh contour in condensed matter physics, in some Schwinger contour in or Schwinger Keldysh in the rest in particle physics. And then that means that in order to write down this low energy theory probably would also have to be formulated in a double contour. It's not a simple like a theory that we have been trying to write down with only one set of fields. It has to be two set of fields.
Right.
That is actually something that people have been thinking about very, very recently. It's one of the original author is a person that you know personally,
Right.
Paulo Glorioso. So that's
Right.
very, very recent.
Right, and I'm aware of the Schwinger-Keldysh formalism for dissipative hydrodynamics. I guess my question was just that even without a Hamiltonian, is it possible to have a Poisson algebra structure or a symplectic structure on the phase space of dissipative hydrodynamics?
I think it's will miss out the fact that what we have here is a doubling of fields. So in principle, there is a instead of there is like with any like row right here, there is a row on the lower contour.
Right.
So instead of a row, there is a row up, like plus minus row down. It's called a delta row.
I see.
So there is a doubling, and it's shown out. I think this becomes, in some sense, hydrodynamics with noise.
Right.
Yeah. So the theory has to be enlarged in scope, and enlarged in the number of fields, enlarged also in terms of what is a set of questions that one can ask. With noise, one can ask not only the question about the relaxation of initial state, but also about the a small thermal fluctuation.
Right.
So we have a theory, but it seems that this theory is complicated, and I'm probably not going to have a very good way to present it. At least I don't know how to make this theory. No, I think in some sense we are going to use this hydrodynamics noise in a somewhat hand waving form later on when we talk about long time tail.
Thanks.
Okay. So next time I'm thinking about going to the next topics of superfluid hydrodynamics. Okay.